we were, at the part that is favorite of the student usually, which is fractals. Let me see if I can share my screen once again, the PowerPoint thingy. So this Feigenbaum constant show a principle of self-similarity that, in a sense, you are pretty familiar with in the context of fractal, or at least I expect you to be, because it's one of the most known things that you can do with the chaos, and the way that most people gets introduced to these concepts is through the self-similar concept, and in fact the fractal look really cool. So this is, for example, the Mandelbrot set. And the nice thing of the Mandelbrot set is that this was a GIF. Should I do it like this? Yes. So as you can see, it's self-similar. If you zoom in into the Mandelbrot set, into a specific point in the Mandelbrot set, and this specific point is actually the Feigenbaum point, which is corresponding to the Feigenbaum constant. So that's a super neat thing. This shows how universal this is. So if you zoom in at the Feigenbaum point in the Mandelbrot set, you show the pattern of the Mandelbrot set repeating over and over again. If you zoom in other points, then you show new and unexpected patterns independently on how much you zoom in. So you have a behavior which is both self-similar and very complicated in something which is fairly simple to define, like the fractal. And this has also implication in nature. So for example, this is a famous example of, I don't know the name of this, kål in Swedish. It's a type of a cabbage, but I don't know the name of this specific cabbage in English, and in Swedish. This is called as broccolo romano in Swedish, in Italian. Somebody probably told me the name in English. Brussels sprout. No, it's not Brussels sprout. Brussels sprout is a small one. It's another type of Romanesco, probably. We call it broccolo romano. So I don't know. Okay, so this is fractal patterns. You can see them in nature very much. And this is because it's a way to maximize the surface given a given volume, because a fractal has potentially, a mathematical fractal has infinite surface for a given volume. Or if you have a line fractal, then for a given length, a total length L, then the length of going through the fractal, since it will go into smaller and smaller structure, that will be infinite. Of course, nature doesn't like infinities or mathematical infinities, at least not when talking about geometrical dimensions. But that's still a way you maximize the surface given a volume. So if a plant is very much dependent on getting as much water as possible for the morning dew, for example, then the dew collects on surfaces. And if you have a large surface, you collect more dew. This is why I think why the broccolo romano gets this much, as this beautiful fractal structure to maximize the dew, but I'm not sure. I'm not a biologist. But so this is why many patterns of these fractal pattern, many things in nature of this fractal pattern, or trees, because these maximize the surface of the trees, that is the light capturing, the leaves are capturing the light, and this is what feeds the tree. So you maximize the number of leaves and minimize the number of leaves. You maximize the surface of the leaves, so the amount of light that you capture, the amount of food that you captured, and minimize the number of leaves that is your objective, because then you minimize the amount of food that you need to provide to the leaves to sustain themselves. So in nature, you have many of these fractal structures, both arising from natural selection, as in the case of the broccolo or the or the leaves on the trees, on some trees, but also other patterns that are given by simply physical properties, because this tension between surface and volume regulates a lot of physics, especially the physics that has to deal with water. So both at microscopic level and the macroscopic level, you have this fractal structure. And in this lecture, we will see how you can recognize if there is a fractal structure in your physical system. So the way you do it is by power laws, and we will see that right now. So basically, this is quite an interesting thing that you have in nature and universal, and you can see it also in the measuring of the coastlines. So this is a nice introduction to how you think about fractals in a sense. So if you want to measure the coast of a country, I found it about Great Britain, and in the book there is a nice example about the coast between north and south of Stockholm. So Söderhamn, and I don't know what the other place is. Valdemarsvik. Okay, sorry if I'm butchering your language. So you have this, this is quite universal in coast, that the amount or the length of coast really depends on the yardstick that you use to measure it. So you imagine like the classical yardstick. So you have a rigid ruler that can measure length. And if you have a rigid ruler, according to the number according to the length of this ruler, you determine the number of measures that you have to take. And so how detailed you can follow the coastline. In the case of Great Britain, for example, if you have only 3 big rulers, then Great Britain will appear like a triangle. And its perimeter will be given by the triangle shape of Great Britain. If you take a yardstick, which is slightly shorter, then you have 9, and this will approximate a little bit better, and you will get more perimeter to represent in the same object. If you have 19, you will get still more perimeter and will represent a little bit better. With 48, you will represent even better. With 97, you will represent even better. And this can go on and on forever. I mean, literally, you can have as long as yardstick as you want, and you will never find out, because at a given length, at a given scale, coastlines are dynamic. So if you take a ruler which is like this, then you will not find the same measure if you do it right now or if you do it tomorrow, because coastline gets eroded, and what's the name of the tides go up and down. So yeah, the sea level goes up and down because of tides. And so this is really important. And it's a kind of field of study. I mean, in geography, they kind of, there were even legal litigations, because according to the length of the coastline, sometimes you had to pay different taxes, and then the yardstick that you use really makes a difference. And then you can have legal battles because you want to measure it with a different yardstick. So this happened for quite a while. Now there is kind of, people have kind of agreed on a way to measure it. But when we didn't have satellite pictures and was more difficult to measure coastlines, then this was an area of research, if you want, that had practical implications. But why do I start by this example is because it's a very neat example to start to see fractals and these power laws, because since you get larger and larger perimeter given by smaller length of your yardstick, or smaller perimeter for larger and larger length of yardstick, you have this behavior will be a function of the yardstick, and the function we will see that is a power of the length of the yardstick, and this power is not an integer number but is a fractional number. Okay, so good. So I did a very lengthy introduction. Let me share. So new share. Oh, you did not see pictures at all. Did you see my screen sharing is paused? So help me now. Did you see the pictures of the Great Britain? Okay, fantastic. So now the sharing is paused, but that's fine because I want to change. So yeah, now you should see the book. And in the book, you can see, for example, the coastline between these two places, north and south of Stockholm in Sweden. And this is kind of a neat example because you see that the distance, the way that this looks like is really similar to this very famous fractal, which is called the Koch curve. And I will show you how to draw it. But before, you can see that the length, the first length of the system that you want to describe is given by the air distance between the two cities in this case. And then this makes up the first approximation. So if you take the air distance between the two cities and you take a yardstick long as much as the air distance between the two cities, then you have a perimeter which is given by the same air distance. If you take a smaller yardstick, which is a third of that, you will see something which is similar to this. You will see that a triangle appears in the middle. If you take something smaller by another factor 3, you will see this sort of structure, and so on and so forth. Okay, so this is a very neat example that the authors of the book picked up about Sweden. So let me now share my iPad so that we have really 15 minutes, but I hope you're still fresh. I didn't do much analytics today. It was more blah, blah, blah. So this is the second lecture about fractals. So the way that you draw these, that is called the Koch curve, is doing like this. So you start, so here he will help to have this activated. So you have this. Okay, this is not really working, but okay. So you have this length like this. Okay, then you divide it in 3 parts. So you take the same length and you divide it in 3 parts, equal parts. And now the one in the middle, oops, okay, this is not as convenient as having a blackbird. Oh, sorry. So you take, if you take a line and you divide it in 3 parts, the one in the middle, you can take an proportionate triangle, so where the lines are all the same. I hope you see my screen. So this is really a bad Koch curve, but who cares? So it's like this, that's fine. So the length here is still L, but this is L3, 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 and L3, okay? So this is L, And this is basically, it's given by 4/3 L, okay? Or 4 times L3. Let's write it in that way. It is even easier. 4 times L3. So this is, I hope, very clear. And then you can go on and on doing the same thing, dividing each segment into 3 and drawing a equilateral triangle. Tac. Also the segments which are, yeah, mine is pretty bad. I hope I was teaching you how to draw a little bit better, but I should take more classes in drawing. Okay. But okay, I show you the proper picture before. So this should be just a linear, but this is how you draw. And the amount of segments here would be 4 for each of the third segments. So if each of these, if you zoom in and you zoom in really a lot, then you see that one of these, let's see if I know, I cannot zoom in enough, but one of these segments, so the first one like this, the one on the right, it's just equal in smaller scale to the one on the left, okay? So it's a self-repeating pattern. So this is also self-similar. So each of these 4 segments that you had now has a 4/3 perimeter. So the yardstick length is now L divided by 9, and the number of perimeters of segments of L divided by 9 is now 4 to the square, okay? So the length now here, basically, if you want to generalize it for n steps and drawing smaller and smaller, in principle even infinite number of Koch snowflake, this is also what happens if you draw it another way. And if you draw it over a triangle, you get the Koch snowflake that is very pretty. So if you do it with a smaller yardstick, in principle even an infinitesimal yardstick, then what you get is that the yardstick length is this, delta n equal to L divided by 3 to the n, okay? I have to deactivate this, okay? And the perimeter is given by Kn, that is equal to 4 to the n, because you will have 4 to the n segments. Here you have 4 segments, here you have 4 square segments. If you divide each of these again into a Koch curve, you will have 4 times each of these 4, that is in turn in 4, okay? So this is 4 to the n, and then the size of the yardstick delta n. So you see that how long the coastline depends on the size of the yardstick, and the length, the perimeter of the Koch snowflake also depends on the size of the segment in the Koch snowflake, the Koch line, Koch curve. That also can generate the Koch snowflake. Okay, so very good. Is it clear? So this is still pretty easy. Do you have questions about this first thing? No? No questions? No questions. Very good. Okay. So what you can see, you kind of get the intuition that this is basically something that can be represented by a power. Okay? So this is 4 to the power n. This is divided by 3 to the power n. This is also 4 divided by 3 to the power n times L. So the smaller yardstick you take, or the more you iterate this function of yardstick, the more the perimeter will increase. And this goes with a given power, with a power that depends on the number of the iteration in this case. But if you want to represent it in function of the yardstick, delta n, so here you have 4 to the n, so you want to simplify this, 4 to the n, and you want to have a power dependency on the yardstick length. This can be done using the properties of the logarithms. I will not do it super in detail, but let's do it the other way around because it's faster. So you want to write this in this way. And so this is the length of the yardstick. It is the length of the yardstick delta n and a constant in front, a. Okay? And the length of the yardstick has to go to some power. I will write it, instead of making a power n or L or whatever, I will write it in this way, 1 minus alpha. Just why not? It just makes it easier. You will see why in this specific case. But in general, this is what is called a power law. So here you say that A is a constant, and then you will see that for the Koch curve, alpha is equal to log 4 divided by log 3. So you can go from here, from here to here, of course, but it's a pain and a half because you have to juggle logarithms. It's easier to do it the other way. So just suppose that you take this as an ansatz that I give you in my infinite kindness, and you kind of calculate that this corresponds to the equation that I've seen above. So this is, I forgot to say that L is equal to L to the alpha. And the length of the yardstick is L divided by 3 to the power of n. And this is also 1 minus alpha. Okay? So this is equal to, you can simplify, sorry, tac. You simplify the L to the minus alpha with the L to the alpha, and it remains the 1. So this is L to the 3 to the alpha divided 3 to the 3, sorry. 3 to the alpha divided 3 is just 1 divided by 3. So I hope this is all clear to you, that I can do this. So it's already boring as it is. So this is given by 3. If I substitute alpha here, this is logarithm of 4 divided logarithm of 3 divided by 3 to the n. And this is equal to L, again, and 3 to the power of logarithm of something is given by the argument of that something. So this is given by 3 that you had divided by 3, and then the power of logarithm of 4 divided logarithm by 3 will get translated as 3/4. Okay? Maybe 4/3. So that's like this. Sorry, not 3/4, but 4/3. Yes, to the power of n. The 3 and 3 simplifies, and then you're left with exactly the equation that we've seen above. Okay. So in this way, I demonstrated what I wanted to demonstrate. So my Koch curve with a given iteration can be written in function of this power law. And as I promised, this is really, really crucial in physics. So I don't want to go further. So we will see how can you define this and what is called the fractal dimension. The exponent here, this logarithm of 4 divided logarithm of 3, will correspond to one thing that is called fractal dimension. That, as you can see, is not an integer. So fractals have a dimension which is not integers, but we will see it later. So this is what the power law really represents. Represent the process. So let's stop sharing, or let's sharing the text once again. So then you can see different coasts: Great Britain, German, West Coast, Portugal. So they all follow these power laws. So this is the logarithm to logarithm graph of the yardstick length and the total length, the perimeter of the coast in kilometers. And you see that different coasts have a different exponent. And this exponent will be the fractal dimension. How much fractalized, in a sense, is the coast? And as you can see, Britain is pretty fractalized. Portugal is also fractalized because it follows the mountain. This is the length of the mountain. Australia is fractalized. South Africa is not fractal at all. So you have that this behavior will tell you how much fractalized, how much self-similar the properties of the coast of a country, in this case, is. So you can do a fit and then find out by power law, by the virtue of the power law, it is really simple, how much self-similar a given thing is, a given coast, in this case that I've shown you, but it can be how much fractally water molecules aggregate under certain conditions. That can be, there was one that did the presentation at our division like in January, and he studied how fractal do water molecule aggregates together, but at the level of few molecules. So 4, 5, 20, 50 molecules have many power law structures. And this is also an indication of a fractalization of their structure. And then, of course, you have snowflakes, for example, that are fractal. This is also a manifestation of the fractalization of how water molecule aggregate. And then you have many different things in physics, in geography, in economics that behave in such a way that follow a power law. The famous Pareto Law, the 80-20 principle, maybe you've heard it, that 20% of the people have 80% of the wealth. Inside of the country, in the world, at each and every scale, you have this same distribution that follows this power law. And this is also a manifestation of some fractal characteristics, not fractal, but of self-similar characteristics of the phenomenon that you want to show. Okay? So, do you have any questions? I see that there is one question in chat. So if you think if there are any other questions in the meantime. So the question is, can you have a vertical line in that graph? And the answer is that will not be a function. So if it's purely vertical, it means that there are several solutions for only one level of yardstick. There are different lengths in the perimeter. So this is not the case, and this will not be a function. But you can have pretty vertical lines. Some in the sense that some phenomena have a very steep power law, so they have a very large exponent, and this makes the line pretty much very vertical. How would the Mandelbrot set look like in that graph? So in that graph, that's a good question. the Mandelbrot, well, it would like, I don't know respect to the coast of Britain, but the Mandelbrot set has its own dimension. So in that graph, you will have, the Mandelbrot set is a fractal, so you will have exactly a line, because that's the structure of a fractal, of a self-similar fractal. So you will have basically exactly a line, and the Mandelbrot set will give a steepness. I don't know about the fractal, well, I cannot remember on top of my head right now the fractal dimension of the Mandelbrot set and the ones of Great Britain. But the Mandelbrot set has a dimension that is between 2 and 1, and the ones of the coast, I don't really know. I mean, I don't know Great Britain, the fractal dimension by heart. I'm sorry. But it will look like exactly like this. It will be a power law that is very regular, very stable. And on that graph, I don't want to share it again, but you can see also the circle, how it looks, the circle. And the circle doesn't look like a power law at all. It collapses, basically, in a way that is not a power law at all. Well, it's not a straight line, but it's doing like this. Will stay almost constant for a while, then bend a little bit, and then just go down like this. Because then, I mean, what does it mean to have a different yardstick for the circle? It means calculating the perimeter of different polygons. So you have the triangle perimeter respect to the surface area, basically. So you will have at this, you can also calculate in that way. You will have at the same surface area the perimeter of the triangle, of the square, of the pentagon, and so on and so forth, adding more and more sides. And the more sides you add, the more perimeter you have. But you don't reach infinity, you reach the circle. And the minimum that you can have is 2 in the triangle. And that's not 0, but is the perimeter of the triangle with the same surface as the circle. So this does not have a power law at all. While the Mandelbrot set or fractals in general have precisely a power law. I mean, I just demonstrated you for the Koch curve. This will look like in that graph exactly as a line with a stiffness of logarithm of 4 divided logarithm of 3, that is 1.26 or whatever. Other questions? Since coastline are made of same stuff, atom molecules, won't the fractal dimension approach the same value? I mean, when you start to get down to atomic scale, then it's not a fractal anymore. But that's a good point. In some phenomena, you can have different regimes. So, for example, as you say, if you have, well, I don't know about the coastline, but if you have a phenomena which has 2 regimes, and both of those can be power laws, or maybe it's only one. When you enter the power law regime, then it will have a power law with a given number, and before will not be a power law, or will have a power law with a different steepness. That can really happen, and that happens a lot in economics, that you have different regimes because you have different mechanisms. For small incomes, you have stuff like taxes that for high income are very different and are managed in a very different way in very different countries. So you have different power laws that starts to be a little bit of a jigsaw, and at the given point start to lose meaning, but it's a good general principle. Or geography, like town sizes are also follow this Pareto distribution that is a power law regime. You have very, very few towns, cities with a very large population, and many cities with a small population, and this will follow also a power law. The population of a city with this frequency in a country. But countries, because of their structure, that can be due to taxes, politics, preference of the population, can clusterize a different steepness, or can have that has very few, very, very large cities and many, many very, very small cities. So you can have 2 different regimes there. So in economics, that's where it's most common, that you have some dimension for one regime for high sizes or for high income, and another dimension for lower incomes. And also, this is also what you see, that for low income, the steepness of the power law changes a lot by the country. And this is what gives you the famous Gini coefficients. So in Sweden, it's pretty egalitarian society. The steepness is not as large as in the US. So this is more of a power law, while in Sweden it's more flat. But then when you get to very, very high income, the very, very rich people can avoid taxes in one way or another. Or their income is not given by that much by how much taxes they pay, because most of their wealth is in stocks and industries, which are not taxed the same way and tend to have a more uniform distribution across all countries. So you have that for very, very rich people, you have to approach the same steepness in the power law in different countries. By us, the normal people have this very different behavior in very different countries. So yeah, you have these kind of regimes. Other questions? No? I'm already over the limit. I started talking about rich people and poor people. I hope that you're in. But okay. So if you don't have any other question, you're free to go. I'm open for other person questions or problems that you have, feedbacks. Thank you very much. I will stop the recording.